This is on. Hello, everybody. My name is Eric Tschetter. I work for Yahoo, doing engineering technically things. And I'm going to talk today about sketching, the future of data processing. Specifically, I'm going to describe kind of an epiphany and a new idea that I ran into when trying to deal with large data sets. And I think it's got a lot of promise for ways of dealing with large data sets in the future, and it all revolves around sketches. And so I call it the new normal, or it's the way that I think over the next coming years people are going to be approaching large data sets to a great degree. And my journey all started with something called Druid. I had the honor of writing the first line of code on Druid. It's an open source project that has a nice set of buzzwords associated with it. It's distributed, horizontally scalable. It's column-oriented. It's highly available, up 24/7. We built it initially in a software as a service company, and so we couldn't really take downtime. It supports slicing and dicing, kind of looking at data, doing data segmentation, and just filtering and aggregation and all that sort of stuff. And lastly, it supports a lot of people eating cake. It's real time. It supports real-time ingestion. It allows you to ingest data as fast as possible and analyze it as quick as you can. And in working with this system, well, first, I'll get some of the benchmarks out of the way, and then go on to more of the story. Kind of some of the reasons to use this system. We have a fairly fast scan rate. This is kind of a naive select count star in a specific time range thing of about 53 million rows per second per core. Our real-time ingestion rate, we can ingest about 20,000 events per second per process. This goes out horizontally, and you can scale it up quite a bit. Cluster sizes, this is the largest cluster as of a year ago. The numbers have not been updated since then, but it had represented over tens of trillions of events and about 500 billion rows on 300 machines. Maintaining 95th percentile query latency under 1 second with 3 million events per second ingested at peak in real time. And so, yay, it scales and does stuff like that. But in working with this system, even though we have all this scaling and you can add machines and do all of this nice, wonderful stuff, data still gets pretty large. Let's say you're ingesting 10 billion rows per day, 100 bytes per row. That's still 1 terabyte of data every single day. Let's say you have a 3-year retention on that. That's a petabyte of data. And people come to you and they're like, I don't want to pay for enough servers to query a petabyte of data. That's too much. Can I get the majority of the answer I want and not pay as much? And this is a question that has been asked in BI and data warehousing and data processing circles for a really long time. And the traditional answers are, yes, you kind of can. We can do one of two things. We can sample the data, shrink it down, or we can do something called summarization. In the Druid world, we generally take the summarization approach, but when comparing these options, I tend to think of it in terms of 3 kind of trade-off spectrums. 1, fidelity. Can you get the full set of answers for your questions? Do you have the full range of the data available to answer whatever questions are there? Size, what's the size of the actual data? And I wrote accuracy here, but of course 5 minutes before the presentation I realized I should have called it correctness, but there's correctness, accuracy. How good are your answers? Are they correct? When you're dealing with raw data, your fidelity, super high. You can answer everything because you have the raw data. You haven't thrown anything away. The size, also, you're paying for everything possible, and your accuracy, it's accurate because you have 100% of the data. When you go into sampling, you get this kind of weird fuzzy thing on fidelity and accuracy. Your size is great. You can control that. You can really operate that. But with the fidelity and accuracy, the reason I kind of have that blurred like this is you run into this issue where based on the axis that you sample on, you can get, if you're asking questions according to the same axis that you're sampling on, you can get great answers. You can get super high accuracy, great fidelity, and get great visibility into your data. But if you sample on one axis and then you're querying on a different axis, you can all of a sudden not be able to understand any true error bounds on top of your data. Like if you're sampling based on users individually, and then you're asking questions about the global set of things that then you're asking questions centered on events that happen rather than individual users, there can be questions that arise about, well, are you sampling correctly for the questions you're answering? And then, or you're asking, and then you start getting into needing to do stratified sampling and other things like that in order to make sure that what you're sampling on lines up with the questions that you're intending to ask. And so sampling can be tricky. It can be awesome, and it can also be less than awesome. With summarization, you have a fixed point more. You throw away some set of data, reducing the fidelity. You can't answer some of the questions that you could have with the raw data. You also have a fixed size point. It's usually, it can be as good as sampling. Sometimes it's not as good as sampling. It depends on how you choose things. But the point of this is more that it's a fixed point. And your accuracy, though, is still high. For any question that you have the data to answer, you get the correct answer. It's always right. So what I'm going to introduce, or kind of the thing that we've started using a lot in order to try and play with this spectrum, is actually summarization with approximation. And here, we actually reclaim some of the lost fidelity from throwing away certain dimensions. It increases the size slightly, but it also, we pay a slight accuracy trade-off. We added approximation for some of our answers. And that's what I'm going to go into a little bit more. So what is summarization with approximation? To get into that, I'm going to do a real quick refresher on what is summarization first. Probably everyone in the audience already knows this, but just to make sure we're on the same page, let's assume I have this data set, and I want to ask questions like, how many impressions were there to a specific domain? How many clicks did a specific gender do? How many female users visited ultra.com? In order to answer these questions with this data set, you first have to understand the data set. So what is this data set? This data set is roughly, this data set is representing ad impressions. Each row is one ad impression. We have a timestamp, when the ad impression happened, the domain that the ad impression happened on, the user that saw the ad, what gender they are, and whether or not they clicked on it. So with this raw data, I can answer all of these questions pretty easily. How many impressions were there to each domain? Well, Bieber.com had 1, 2, 3. It existed 4 times, so there were 4 impressions on Bieber.com and the others, and so on and so forth. You can see how you can kind of figure out these answers. So summarization, let's say I want to summarize on the hour. It's real simple. I throw away everything except for the timestamp down to the hour, and I see that all of these things happen in the exact same hour. So my 10-row data set now became 1 row with 10 impressions and 6 clicks. Now the thing is, I can't answer questions about the domain, about the user, about the gender anymore, because I threw all that data away. So what happens when I reintroduce it? If I reintroduce gender, my 10-row data set has turned into a 2-row data set. It's still a pretty nice reduction, and now I can answer questions about genders. Great. If I reintroduce domain, same thing. My 10-row data set becomes a 2-row data set, and I can answer questions about the domain. But I can't answer questions about the domain and gender. So if I reintroduce gender as well, now my 10-row data set becomes a 3-row data set. And you'll notice that Bieber.com is never visited by males because I made up this data set and wanted it to be fewer rows. But anyway, so the idea here, though, is that while the actual potential number of combinations is 2 of the domain and 2 of the gender, meaning you could have 4 rows. Because one combination doesn't exist, our data set doesn't have it. And so we only have 3 rows rather than the maximum potential number of rows, which would be 4. But now, let's say I want to reintroduce user. Turns out there's only one collision in my made-up data set with users, which means that I don't really get much space reduction. There's only this one repeat. It's only, my 10 rows only goes down to 9 rows. And so reintroducing user actually explodes my data set back out again and forces me to, once again, pay a lot more money for storage. So to kind of summarize this, summarization gives you the ability to, or it changes kind of how your data set grows to be based on the number or the interplay, the interrelationship between the dimensions that you choose to include and not necessarily the actual input set of your data. So you could have 1 million rows coming in, and if all you care about is gender, you're still only going to get 2 rows coming out because, well, let's assume there's only 2 genders, but well, you're going to get 2 rows coming out assuming there's only 2 genders. Anyway, you lose some fidelity. You lose the ability to ask questions about all the things you threw away, which is kind of unfortunate, but you know, it's a trade-off spectrum. Someone came to you and said, I don't want to pay as much. What can you give me if I don't pay as much? So you tell them, I can give you this. But now, in this world, wouldn't it be great if we could reclaim some of that lost fidelity? If we could answer questions about how many unique users existed? Well, it turns out we can. And the simple, naive approach to doing it is, well, we don't have to have the user IDs as a dimension. We can store it as a metric. We can basically have a metric over here, which is the set of user IDs that appeared inside of this dimension tuple bucket. And then at query time, we can union these sets together, and I can tell you this is how many unique users there were. So I can still answer questions about uniques, even though it's not a dimension. Great. But now you're going to look at this, and you're going to say, oh, wait a second. That uniques thing grows linearly. That could take a lot of space, and that's true. If this set, if the number of uniques happened to be 1 million or 1 billion users, I would have a set of 1 billion user IDs hanging off here, and that's going to be pretty large. Depending on how you're processing things and depending on the size of your machine, it might actually be too large to fit in memory, and you're going to have to do a whole bunch of stuff to work around that. So now the question comes down to, can we limit the memory required to store this set? What can we do to limit that memory requirement so that we can still answer questions about the uniques, but also not have to pay for storing 1 billion things if our number of uniques happens to be 1 billion? And so essentially, we want to replace these sets with, I'm using the technical term here, a nonlinear thingy. So what are the requirements on this nonlinear thingy? We want to provide answers to how many unique things did you see. We want to limit requirements, and we want it to be combinable or additive. Turns out there's these things called sketches, which kind of fit this bill. Theta Sketches is what we use at Yahoo, is developed at Yahoo. But the basic idea is we can do all of these things as long as we take the trade-off of approximate answers. And so we can replace those sets with these sketches and just get approximate answers. And so when I say approximate answers, what am I talking about? Well, it's parameterized, so you can adjust a parameter to figure out how much error. 2 standard deviation error, using 32 kilobytes of memory, you'll get 3.13%. Using 128 kilobytes, 1.56. And it kind of goes on like that. Once you're at 512 kilobytes, you'll get 0.75, and on and on and on. There's a nice little error table here that can be accessed to see all that stuff. But anyway, so how do these sketches work? What's the kind of high-level idea? Basically, they start with hashing an identifier. You take your user ID, you hash it. This hashing essentially remaps the identifier onto a random distribution. onto, if you think of the output of the hash as a number between 0 and 1, then you essentially have just random numbers inside of that 0 and 1 space. You then take that randomly distributed number and you store some model based on that hash. With hyperlog, which is something else we use, you do one thing. With this KMV, which theta is actually a variant of KMV, you store the K minimum values. But anyway, the high-level idea is you build some model based on the results of these hashes. You store that model. That model is the thing that's additive that you can combine between other models. And then you use that model to actually estimate your cardinality. So Theta Sketches, which I'll describe a little bit, kind of at a high level, it's part of this Data Sketches organization on GitHub that is operated by some of us at Yahoo. It's open source, Apache licensed code. It's been developed primarily, the algorithmic stuff was developed primarily by Kevin Lang. A lot of the code has been done by a guy named Lee Rhodes that I work with. I'm just a guy that thinks this stuff is cool and kind of integrates it with other things and gets to talk to you about it. But these guys are they're the actual brains behind a lot of this stuff. And there's actually a paper that they just recently announced at, or they just recently presented at, I forget the conference. It's a theoretical computation conference that was in France last month or 2 months ago. But anyway, there's a paper about it. You can read about all the mathematics and everything about it if you're interested in that stuff there. So what's the high level? How does this thing work? How can you limit the memory but still get good answers? And in order to describe that, I'm going to use a concert line. Now let's say you're standing in a concert line and you want to know how many people are in this line. How long am I going to be standing here? Because this looks pretty long. You're going to say, OK, I can see the line is a city block long, and I'm at the very end of it. And I know that, I'm 2 feet from the curb. So I might make the assumption that, well, if I'm 2 feet from the curb, then maybe the next person in front of me is 2 feet from me, and the person in front of them is 2 feet from them. And I'll say, OK, every person is consuming 2 feet. And so I can come up with an estimate of, OK, 1,056 feet in a city block, 2 feet per person, 528 people. Turns out this is an estimate. It turns out this isn't such a great estimate. Now, why is that? Well, you have these couples ahead of you that are kind of, standing a little close to each other, doing the couple thing. You've got these dreamers, that guy who's just staring off into space as the other people in front of him walk ahead, and there's all this extra space there. And so you've got this kind of variability in the actual spaces. So everyone is not actually 2 feet apart. So what you can do is you can say, well, I can see ahead 10 sidewalk cracks. And when I look 10 sidewalk cracks ahead, I can see that there are 11 people inside of those 10 sidewalk cracks. So one sidewalk crack is 3 feet. I just know that because I don't know why, but I do. And there's 11 people in that. So let's say for every 30 feet, I have 11 people. Now my city block, 1,056 feet, there's 35.2 chunks. 35.2 chunks with 11 people is 387.2 people. And it turns out this estimate is probably a lot better than this estimate. And the basic idea here, though, the high-level idea to take out of this is if you think of the curb as your 0, the end of the city block as your 1. And when you hash values into this space, they're going to hash inside of it in variable densities. There's going to be some parts where they're really close to each other, and some parts where individual values are far away from each other. But what you can do to limit your memory size is essentially, as you hash more and more values, you can shrink how much of the space you look at. And as long as you keep enough values in the space you're looking at, you can accurately, or you can generally look at the density inside of that space, use that to then approximate the density of the entire space between 0 and 1, and get really nice answers really nice approximations of how many things were actually inside of this space. And so we take the cardinality question and we turn it into a density question. You have a sample rate that basically decreases as you get more things that enter into it, and then you just ask, how dense is my current sample? How many samples are there in the full set? Yay, that's my value for cardinality. So there's other sketches also inside the repertoire of the Data Sketches library. We have a tuple sketch, where let's say you have these IDs for users. You can attach a payload to them, some value. You then use normal theta sketching things to kind of shrink down your set as you add more users and do all of that. And at the end of that, you end up with a sample of users that have this payload attached to them. You can then analyze those payloads, knowing your sample rate, apply that sample rate back to the analysis and say, OK, this is an approximation of the values on these payloads. And so you can do things more than just cardinality. You can start to get distribution, user-style distributions and other things out of the data. We also have quantile sketches, where let's say you're looking at query latencies and you're building up your query latencies for every hour. If you just take the total query latency and the number of them, you can figure out the average, but you can't figure out the distribution. In order to resolve that, we sketch the distribution of the numerical values. And the algorithm that we have implemented basically allows you to ask questions. So you build this sketch. You can then ask questions. What was the value at the 90th percentile? What was the value at the 50th percentile? What was the value at the 99th percentile? Whatever. You can also say what percentile was value 10. So you can take this distribution, this sketch, and you can build human understandable histograms out of it. Because humans don't really like to look at log definitions of histograms. Humans want to see what's 0 to 1, what's 2 to 5, what's 5 to 10, and all of that sort of stuff, or at least the non-technical humans anyway. Some kind of parameters of these sketches, we can store 4 billion entries. So 4 billion entries coming in of query latencies. We can maintain a distribution that will maintain 1% error in 51,000 bytes. And so that's significantly smaller than 4 billion bytes, assuming that each entry is just a single byte, even though it's probably an int or a long or a double or whatever. Anyway, so this can really shrink down the data, but still give you answers. It can reclaim some of that fidelity lost by summarizing and aggregating the data together. And so, in conclusion, kind of the big thing that I want you to take away from this, other than we have this Druid thing and this Data Sketches thing, and they're open source and you could work with them and all of that stuff, is when you're doing summarization, one of the big downfalls is you lose fidelity. People don't like that loss of fidelity. But you can leverage sketches. And there's this whole area of research and body of research and algorithms that can be leveraged to reclaim that fidelity. And really, any additive data structure is a candidate. And you can approach a lot of these problems where I lost something during summarization. How do I get it back? You can start to look at that and think, OK, is there some approximation algorithm? Is there some data structure that I could store this in that would allow me to answer some of those questions still without paying the full cost of storing all of that data? And to me, I think this learning about sketches, learning about how they can be used in data with the summaries has been very eye-opening, and I see a lot of potential in the future for leveraging this to make data accessible, shrinking data sizes without giving up the ability to answer questions about stuff. And that does it for my presentation. I have no clue how much time I took or how much is left. So I have 5 more minutes. So if there are any questions, yes?
So I know whether the just-in-time oracle. So I know whether your example of the list of users comma separated was a hypothetical example, but what does lossy mean? Because would it mean that I would still get a comma-separated format and that, you know, some of the IDs would be incorrect? Or does it mean that instead of commas, it would be exclamation marks, and therefore I need to sort of figure out, you know, how I then turn that into a set of IDs, if you like?
Sure. So the question is, if I can repeat it and make sure I understand, when you have this setup,
What does lossy mean?
so when it's this setup, it's not that lossy. You can extract out all of the, you can basically, you can get back to this from this if you go and try and extract things and figure it out. You can actually do that. Once you go into the sketch world, you basically have taken these IDs and you've hashed them and thrown away the initial ID.
Okay.
And a lot of times also, depending on the sketch, you throw away some of the actual inputs as well as you go into the sketch. And so you don't have the original ID anymore. So this representation is actually not necessarily lossy, but once you enter the sketch, you cannot go back to the original user IDs.
It's still lossy because you lost the minutes to the hour.
Yes. Well, yeah. Here, yeah. I've summarized away the minutes. Yeah. That's correct. It's lossy because you can't get these milliseconds.
Oh, okay. So it's not lossy for the IDs. Okay.
Yeah. This representation is not lossy for the IDs.
One more question?
Any other questions? There's one, two.
So what happens if you get, so what happens if a user ID isn't just an ID? And, you know, let's say 2 years down the line, you get some extra information about that user, like what's their eye color. If you've got the ID still, you can go and get you get this extra attribute
Yes.
to your data set. Is there any way using sketches that you would be able to recover that, get hold of that attribute from the sketched representation of the ID?
No. Once you go into the sketch, even if you later on learn that a specific user ID has an eye color of a specific thing, you cannot, there's no way to actually go back and annotate the data. And so generally, like the way we use these algorithms is there's a data warehouse that exists somewhere that has the raw data in whatever data warehousey storage format. And we can go back to that and regenerate this data. For this data, we're generally storing a faster access kind of aggregate view that is kind of trying to do 80%, 90% solution type stuff, where we can answer certain sets of questions faster than going back to the actual data warehouse.
All right, so let's thank Eric because we are right on time. So there's enough time during the. All right.